This is Pre-Calculus, Section 2.4 Notes, Day 2. We're going to continue talking about transformations of functions, and today we're actually going to apply it to some real parent functions that we are used to working with. In example 1, we want to graph y equals the square root of x plus 3. So our parent graph here is just this part right here, the square root of x. And hopefully you don't have to make a table for that. Hopefully you know what the basic shape of the parent graph of the square root of x looks like. It begins at the point 0, 0. It has a point at 1, 1. And it has a point at 4, 2. And then if our graph continued, it would have a point at 9, 3. Okay, so this is, I'm going to label this P. This is our parent graph. So then that plus 3 that we see at the end of our graph, that's going to be a K value, or that's going to be a vertical shift up 3. So then we're just going to move each of our key points here up 3 units. And that's my final graph, so I'll label it F for final. In example number 2, notice that our parent graph here is going to be the absolute value of x. So right here, oops, that's our parent. So once again, if I just make a quick sketch of the absolute value of x, I know it looks like a V, and the slope of the right-hand side is positive 1, and the slope of the left-hand side is negative 1. So there's my parent graph. Okay, so now I've got 2 transformations on this one. So it looks like on this one I am going to be doing a horizontal shift because I've got an h value of negative 3. Okay, so that tells me 3 to the left. Remember, it's always opposite of what you see. And then I've got a k value of negative 1, which means that I'm going to be moving down 1. So I'm just going to take each key point and I'm going to move it 3 to the left and 1 down. Start with that vertex. And once I move the vertex, then I know that the general shape of the graph isn't changing at all because I don't have an a value here that's stretching or shrinking anything. So I can just go ahead once I plot that vertex of my absolute value, and I can go ahead and plot the graph from there. So this is going to be my final graph. The last example in this question is a really important one. And it says right here, it might help to rewrite the equation. So notice, first of all, that this kind of looks goofy. Okay, I'm going to put y equals. That 2 in front is really a k value. So I've got a negative 1 out in front, and then I've got x minus 3 quantity squared, and then I'm going to put that plus 2 at the end. So the first thing is my parent graph here is y equals x squared. And I know what that looks like. That's got a vertex at 0, 0. Remember, it's got an axis of symmetry right on the y-axis. It has a point at 1, 1, a point at 2, 4, a point at 3, 9, so on and so forth. But this is enough here. So these are the points that make my parent graph for y equals x squared. So again, label that with a P. Now, the transformations here are important because order of transformations matters. So we are going to write this down. But first, let's just write down what our transformations are. Now, it's really important with transformations. We kind of follow PEMDAS, but we start on the inside and we work our way out. Okay, so when we do this, as you can see, if we start on the inside, we've got that x minus 3, which tells us we have a shift 3 to the right. Then the next thing would be the negative 1 out in front. That's going to be a reflection over the x-axis. And then the third, or the final thing, and the third thing is that shift up 2. Okay, so again, I'm just going to write down here before I do any graphing, order transformations matters. And I will do an example in class where I will prove to you why it matters that you do things in the right order. So again, first we are going to do any horizontal shifting. Then we're going to do our reflection. And then we're going to do our vertical shift. And if you find this confusing, just take it one point at a time. But you can see the order of transformations by considering PEMDAS when you look at the equation. Okay, so let's do this. Let's start with our vertex, which is at 0, 0. So we're going to shift it 3 units to the right. Then we're going to reflect it over the x-axis, which it's on the x-axis, so it's not going anywhere. But then we're going to shift it up 2. So that point is going to end up right there. Then I'm going to look at the point 1, 1. First, we're going to shift it 3 units to the right. 1, 2, 3. And then we are going to reflect it over the x-axis. And then we're going to do our vertical shift up 2. So that's going to be right there. So then you can kind of see that that symmetrical point across from it is going to be there. Now let's look at this point 2, 4 on our parent graph. We're going to take that point and we are going to shift it 3 to the right. 1, 2, 3. So it's right there. Then we're going to reflect it over the x-axis. Okay, so then that's going to put it way down here. I'm right down here right now. Whoops. And then we are going to shift it up 2. So that's going to land that point right there. So that right there is going to be my final graph with these 3 transformations applied. The next thing that we're going to talk about quickly is even and odd functions. Okay, even and odd functions have to do with symmetry of the function, and we're going to talk about how you determine it and then also visually what these examples look like. So first of all, if you have an even function, what that means, and I'll explain this more carefully in a minute, is that f of negative x is equal to f of x. So algebraically, what you are going to do is you're going to replace x in your equation with negative x, everywhere that x appears. And then you're going to simplify. And in order for this to be an even function, you must get the same function. Even functions are always symmetric with the y-axis. So an example of an even function that you all know would be f of x equals x squared. We were just transforming that a moment ago. So this is an example of an even function. When you plug in negative x values, you get the same thing. So if you plugged in negative x and squared it, you would get the same result as if you plugged in positive x and squared it. That's what it means to be an even function. Odd functions, on the other hand, when you plug in a negative x value, what you get back out is the opposite of the function, or negative f of x. Again, you're going to do the same thing. You're going to replace your x values with negative x in the equation, and you must get the opposite function. Odd functions are always symmetric with respect to the origin. And an odd function that you are familiar with is f of x equals x cubed, which looks kind of like this. Okay. That is symmetric with the origin. So it's almost as though if you rotated it around like 2 quadrants, you'd end up with the same function. So for the last examples, we're just going to do some algebra to determine whether the function is even, odd, or neither. We don't have to graph these. We're just going to look at this algebraically. So whether it's even, odd, or neither, it doesn't matter. We start these problems the same way. Our first step is going to be to replace x with negative x, or to find f of negative x. So in the function, wherever x appears, you are going to put negative x. And then we're going to simplify. Well, we know that negative x cubed means negative x times negative x times negative x. And then minus negative x, chop, chop, that's going to become positive x. And then finally, negative x times negative x is going to give us a negative x cubed plus x. Well, if you take a look at that and compare it to our original function, what if we factored out a negative 1? Then this would become positive x cubed minus x. So you can see, in conclusion here, f of negative x is equal to negative 1 times f of x, which tells us that this is an odd function. In our last example, we are going to do the same thing. We are going to find f of negative x by plugging negative x in every location where we have x in our function. Be very careful here with your parentheses. Excuse me. And now we're going to simplify. Negative 3 times negative x is going to give us a positive 3x. And then we have our minus sign. And then negative x squared means negative x times negative x. So then we have 3x minus negative x times negative x is going to make positive x squared. Well, if we look at that and we look at the original, okay, if we factored out a negative 1, yes, that would make our 3x negative, but would make our x squared positive. So what that tells us is that, and I can show that work here, if we factor out a negative 1, this becomes a negative 3x, but this becomes a positive x squared. So what we can determine from this is that f of negative x does not equal its original function f of x, and also f of negative x does not equal the opposite of f of x. So if it's not the same and it's not the opposite, then what that tells you is this function is neither an even function nor an odd function.